Good evening and welcome to day 4 already of the CSET 3 workshop. Can you guys hear me? Okay, perfect. So far there's only 2 of you guys online, so let's give it another minute and hopefully we get some more people showing up. Okay, so let me start recording here. So today we're going to talk about limits at a point and then continuity. There's plenty of definitions in the notes tonight. I'm going to very quickly go over them. It just means it's if you know one of them, if you have an understanding what it means, then no matter which one I write down, you could at least in words come up with your own definition of what that means. Okay? So let's start with limits at a point. There are several types of limits, but before we do anything on limits, limits are arguably one of the worst understood things or concepts in calculus. Limits seem to be this thing that, do I really need to know it? And yes, they are used in the development, the proofs of calculus, but they're also very, very practical concepts or tools. So in that sense, everybody who takes calculus should understand what a limit is. So let's first go over that before we learn how to calculate what a limit is. So a limit, I think of a limit as a prediction. So the limit of a function f of x as x approaches 5. What does that mean? We're asking, what do you think f of x is as x gets arbitrarily close to a? What does that mean? You get very, very close to a, but you are not equal to a. Okay? So intuitively, you predict what should f of a be based on values of f of x when x is not a. So we cover up what happens at x is a, and I'm asking you, what do you think is happening at x is a? It is absolutely not important if what you predict is happening is really happening or not. You're just making a prediction. Okay? So, as is the case a lot of times in calculus, whenever we introduce a concept, it tends to be the easiest tends to be to show it on a graph. But we would like to be able to calculate things. Calculus. Okay, so first we learn to see them on a graph, and then we learn how to calculate them. But don't ever forget the graphical part, because that's where the understanding comes from. Tonight I will also use once in a while a table to evaluate limits. A table is something that you should not use. Okay, why? Well, first of all, it's a ton of our calculations, and it's not very accurate. But so then you might wonder, why on earth are you going over it then today? It actually helps us to illustrate the concept of a limit, And it will also teach us also that's how you do it practically, based on those tables. But so then later, whenever anybody asks you to evaluate a limit, you should not use a table unless that's what they're asking for. Okay, so we start with a one-sided limits of a function as x approaches a number. Most textbooks start with two-sided limits, and then they say something like, well, you could now do the same for just one-sided limit. That approach to me never made really sense. Why not start with one-sided limits and then just say, now if you do both sides, then you get a two-sided limit. So I'm going to go with that approach. So let me spell out one definition for in detail for the limit from the left. So what is the idea here? We have a function that is defined in an interval of the form a number comma a, where a is that given number. So what does that mean? Your function is defined to the left of a. If a was 5, then your function must exist for values less than 5. Otherwise, you cannot talk about the limit as x approaches 5 from the left. Okay, so we have a function like that, and we have L is a real number. What is our word definition of the limit of f of x as x approaches a from the left is L? The notation that we will use for that is this here. So let's go over that notation. Lim stands for limit. X arrow a means x approaches a, whatever that means. And that exponent, that negative sign, means from the left. F of x, that's our function, is equal to L. So the limit should be L. The output is L, the input is approaching A. Approaching in general means getting close to it. So that means that f of x, the values of f of x, will get as close as possible to L. They could be equal to L even, when x approaches the number A. That means x gets arbitrarily close to A, but x is always less than A because we're approaching from the left, and x is not A. I can't stress that out enough. X is not A. The limit as x approaches A always means that x is not A. Okay? So it just means if x gets very close to A from the left, then f of x should be very close to L, possibly equal to L. So that's the limit as x approaches from the left. What would be the difference if we say the limit as x approaches A from the right? So what would change in this definition? Well, as x approaches A from the left, x needs to be less than A. If x approaches A from the right, what will have to be true? X will be bigger than A. Okay, so if I look at all of this, I will need to make sure that my function exists to the right of A, and then just replace less than with bigger than. So here's that definition. F of x is a function that is defined to the right of A. L is a real number. We say that the limit of f of x as x approaches A from the right is L. Notation, limit x arrow A plus to indicate for the right. F of x is L. What does that mean? F of x should get very close to L as x gets very close to A, but this time x is bigger than A and still x is not A. Okay, so we can see one-sided limits on a graph of f. Okay, so I will project a picture there and then we'll look for some limits. So here's a picture and of a function f of x, and I would like to know the limits here that are mentioned here. So the limit as x approaches -1, what does that notation mean again? Exponent minus sign means from the left. So how do I explain that to my students in calculus? I say, get on the graph to the left of -1. So here is, I'm on the graph, I'm at -3, so that is less than -1. And now let your x-coordinate approach -1. So start walking to the right, but you gotta stay on the graph. Okay, I start walking, I start walking. As I get closer and closer to -1, what's happening to my y-coordinate? And if I get extremely close to -1, but not equal to -1, what would you think my y-coordinate is? You would think that it's 3. You would not say that the y-coordinate is 1. What did I do wrong if I think that it's 1? Huh. Then you looked what happened when x is equal to -1. But in the limit, we don't care that about what happens when x is -1. We're making a prediction. What do you think happens when x goes to -1? Here's a very practical way of doing this if you have a problem with this, is pick a piece of paper. So we're looking at the limit as x approaches -1 from the left. So take your graph and cover up everything to the right. So that means pretend there's a piece of paper here. You don't see it. So the only thing that we see of our function is it looks like this. And now I'm asking, what do you think f of -1 should be? Well, you would say, I think that it's the y-coordinate of this point. So the y-coordinate of whatever that point is. So if I now go back to the actual slide, I think I'm ending up over here. What is the y-coordinate of that point? 3. So we think that the limit as x approaches -1 from the left is 3. Everybody okay on that? So we're just doing a prediction. Is that equal to f of -1? No, but that's not important. Based on the information when x is not -1, you think it should be 3. Okay, now let's do a whole bunch more like that. What is the limit as x approaches 2 from the left of f of x? I get on the graph as x is approaching 2. To the left of 2, somewhere here. I start walking towards 2. Closer and closer, but not equal to 2. Where do you think I end up? What are the coordinates, x and y, of the point where you think we end up? We think we end up at 2, 2. That's where we end up, right? Seemingly. So the limit would be equal to 2. We think that we end up over here. Is that where we really end up? In this case, yes, but that's absolutely not important. So make sure to understand what would happen if I change this graph and make this an open circle and put f of 2 here? What is the limit this time as x approaches 2 from the left? It is still 2. It doesn't change because the information of what happens when x approaches 2 doesn't use what happens when x is 2. So it doesn't matter what x is 2, what happens when x is 2. The answer is purely determined by this part here. And that part tells us that we think we end up at y coordinate 2. Okay, so let's do more. The limit as x approaches 5 from the left. So I get on the graph somewhere to the left of 5 here. I start walking. I think I end up here. Its y coordinate is 3, so we think that the limit is 3. The limit as x approaches negative 1 from the right. Is also 3 because I get on the graph somewhere to the right of x is negative 1. I get closer and closer to negative 1 staying on the graph. I think I'm ending up here, whose y coordinate is 3. The limit as x approaches 0 from the right. That limit seems to be 0. We get on the graph somewhere to the right of 0. We start walking, let x get closer and closer to 0, but not equal to 0. I think I end up here. Again, you can cover this up with a piece of paper, put the piece of paper on the left and on top of the y-axis. Where do you think you end up? We end up 0. The limit as x approaches 2 from the right. So we get on the graph to the right of 2. Let x approach 2 from the right. We think we end up here. So that limit is 0. The limit as x approaches 5 from the right. We get on the graph to the right of 5. Let x approach 5. We think we end up here, whose y coordinate is 3. Okay, so when we look at all these examples, in some cases, the limit from the left and the limit from the right are not the same. Like at negative 1, where is a point where the limit from the left is not the same as the limit from the right? So let me write x is 2. There's something, the limits are not the same, right? Sometimes at 0, there's also something weird going on. The limit on the right is 0. The limit on the left we haven't defined yet, but it's not the same. And then sometimes they are the same, but we're not the function value. Where does that happen? That the limits one-sided are the same, but not the function value. At negative 1, we got the same limit, but it's not the function value. So let's say x is negative 1. There's something with our limits there. How about 5? At 5, left and right is the same, and it is equal to the function value. So if I would now ask you, At which points on that graph is there something weird going on with f? What would those x values be? So could you list all the x's at which you would say there's something weird going on with that graph? At -1, there's something weird going on. At 0, there's something weird going on. At 2, there's something weird going on. Would you say that there's something weird going on at 5? No. So if the limits are the same and it's the function value, there's nothing weird going on. At 5, there's nothing weird going on. But at the others, something weird is happening. So this is more, what is the use of these limits? Well, if we could evaluate those limits somehow, then we would be able to tell when something weird is happening with our graph. Whenever the limits are not the same or not the function value, something weird is happening with your graph. And that's the whole point about these guys. So this exercise were more about recognizing one-sided limits on a graph, but it also already tells us, hey, these limits might help us if we could only figure out a way to evaluate them. We call those limits finite. Why? Because the answer was a number. You could also define one-sided limits when the output is infinite. Okay, so how would that work? Well, here's an infinite limit from the left. So, same setup. We need to have a function that is defined to the left of the number a. And we say that the limit as x approaches a from the left is positive infinity. The notation will be the limit as x approaches a minus of f of x is infinity. What would that mean? It would mean that the values of f of x get close to infinity. What does that mean, close to infinity? That means you're a very big number. So it means you get arbitrarily big. If the values of f of x increase without bound. That's how you might see it in books. What does that mean is f of x gets arbitrarily large. As the values approach x from the left, so x is less than a, x is not equal to a. So there's that distinction between what's happening to x and what's happening to f of x. F of x could go to a number, or f of x could go to infinity. X could approach a number a, or x could approach infinity. And you're absolutely right, that would be then the definition of x is equal to a is a vertical asymptote. What does it mean for the graph? Your graph should go all the way up as x approaches a from the left. So here's how that should look like, seemingly. And when I approach the next slide, we're going to lose this. But so here's somewhere the line x is equal to a. As we approach a from the left, I should get very big. I should go all the way up. That should be your function. Okay. Similarly, you could make f of x approaching negative infinity. What would that mean? What would be the negative infinity would mean, so here the limit as x approaches a from the left would be positive infinity. Sometimes I write infinity, sometimes I write positive infinity. What would be negative infinity? Just make sure it goes all the way down. Okay, so the definition is in the notes. What's the only difference is how could we say that f of x approaches negative infinity? The values of x increase without bound, get arbitrarily large. Now you should say get arbitrarily negative. So f of x decreases without bound. So f of x gets arbitrarily negative. You should not say get arbitrarily small. In analysis or calculus, that typically means positive and small. So gets arbitrarily negative. But those are only the limits as x approaches a from the left. So you got two more of these definitions when x approaches a from the right. You could have the limit as x approaches a from the right is infinity, or the limit as x approaches a from the right is negative infinity. How would you recognize that on a graph? You have your line x is a. On the right-hand side, this would be going to infinity. And this would be an example of approaching a from the right but being negative infinity. So there's not really any sense in memorizing these definitions as long as you can understand what it means. Okay, so same thing, you can see these guys on a graph. So, okay, so here is again an example of a graph. What is the limit as x approaches 0 from the left? We get on the graph to the left of 0, follow the graph. Oh, I'm going up, 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 up. I increase without bound. I get positive infinity. The limit as x approaches 0 from the right is also positive infinity. The limit as x approaches 4 from the left we get on the graph to the left of 4. We go all the way down, so negative infinity. And the limit as x approaches 4 from the right of f of x is positive infinity. Now, sometimes in calculus or analysis, people say, if the limit, if not a number, it doesn't exist. Technically, that's correct, but it is more information if you tell somebody that the limit is not a number, but it's going to infinity, versus the limit is just not a number or doesn't exist. Those are not the same things. So I prefer, like in most books, that you would write these guys down here. You might have noticed on the graph, at x is 4, the function doesn't exist. So this is really the graph of a function, but in reality, what do people do often? They will draw this line here, x is 4, or x is. They will write it like this. This is not part of the graph of f, but it helps us illustrate it, or it makes it much easier to see, oh, this guy stays to the right of that line, this guy stays to the left of that line. So the reason people graph those vertical lines is because it makes it easier to see, but it's not part of the graph of f. Okay, so now that we're done with the graphical part, let's see this in action on an algebraic one. So this time no graphing. Let f of x be x plus 1 if x is less than 2, and x squared minus 4 if x is bigger than or equal to 2. Could you use a table of values to guess the limit as x approaches 2 from the left and x approaches 2 from the right? So what kind of values would you use if you want to look at the limit as x approaches 2 from the left? Something that's close to 2, but is less than 2. So maybe 1.9. If you want to get closer, what would you use? 1.99, 1.999. Start pretty close already. Don't start with, oh, let me try 0. That's not very close to 2. Okay, what would you use to find the limit as x approaches 2 from the right? As something a little bit bigger than 2. So 2.1. If you want something closer, 2.01, 2.001. Depending on the example that you're doing, you might say, why not immediately take 2.0000001? I'll know it for sure. If you plug them in a calculator, your calculator might not be able to handle it. So you want to start close, but not too close. But so that means now I need to plug in those 6 numbers in my function. Which formula do I have to use for these guys? The x plus 1, because I'm less than 2. How about this guy? The second formula. And my last question before I show the table, what happens if I delete that x is bigger than or equal to 2 and I make it x strictly bigger than 2? Does anything change then? Does that make a difference for those limits? It makes no difference for the limits, because what do we not care for those limits? What do we never use for those limits? At least in the definition, x is equal to 2. We want to make a prediction. What happens when x is 2? We don't care what actually happens when x is 2. We just want to figure out what do we think it is. So here's my table of values. So we plug in all those numbers. Here's what we get. Here's what we get. Okay, based on those tables, what do we think the limit as x approaches 2 from the left is? Conjecture. The limit as x approaches 2 from the left. Well, we're asking, are these numbers approaching something? 2.9, 2.99. That's all the way, that seems to be getting close to 3. What do we think? So based on that information, if I would say, hey, what do you think f of 2 is? Based purely on this table, you would say, I think it's 3, right? Now, you use the second table. What do you think now the limit should be? 0, 4, 1, 0.0. These numbers seem to be going towards 0. Oh, the left limit is not equal to the right limit. From that previous example, there's got to be something weird going on with that function at 0. Okay, so now let's see why this makes sense. Okay, what is the graph of something like this? It's a piecewise defined function. So what do? I need to graph x plus 1, but only when x is less than 2, and x squared minus 4, but only if x is bigger than 2 or equal to 2. So here's the graph of that function. Okay. Now, if I would have given you this as an example, graphically, how would you find the limit? It is indeed a jump discontinuity. The limit as x goes to 2 from the left. The limit as x approaches 2 from the left, you would have said it's the y-coordinate of this point. You would think I end up there. But the limit as x approaches 2 from the right, you would have said it's the y coordinate of which point? This time you would have thought that you end up here. So, now going back to the definition, to our function. If I ask you, here's that line, can you figure out what the y coordinate is of that point? How would you do that? So if I would give you the equation of this line and I ask you what's that coordinate, you would say just plug it in your line. The equation of the line was y is x plus 1. So that is 3, and that is 2 plus 1. You might say, well, wait a minute. You just told me that the limit as x goes to 2, we don't care what happens at 2. Correct. We're just coming up with a way. How did you get that? Well, how can you find out what the y coordinate of this point is? That is practically plugging into the line. Okay? So, and the table on the right, that y coordinate of that point is 0, which comes from, this was, I forgot what it was, x squared minus 4. So if I would ask you, here's the parabola, x squared minus 4, how can you find the y coordinate of that point that I marked? What would you do? You would say, let me plug in 2 in the parabola. I would get 2 squared minus 4. Okay, so it seems, how would you evaluate this, a limit with this function? Well, if you approach 2 from the left, plug it into the top formula. That would be this guy. But if you want a limit of bigger than 2, you're still plugging in 2, but you plug in 2 into a different formula. So that would just be like, okay, here's our algorithm. Here's what we do if we want to find the limit as x approaches 2 of such a function. Plug in 2. In which one? Well, that depends on which limit you are looking at. It does not depend on it being an equal sign here. We're just coming up with a way. The limit as x approaches 2 from the left, use the formula x less than 2. The limit as x approaches 2 from the right, use the formula x bigger than 2. All right. So that's good to remember. All right. Let's use a table of values to guess the limits as x approaches 0 from the left and the right of 1 over x. What kind of values would we use for x to find the limit as x approaches 0 from the left? We would use negative 0.1, negative 0.01, negative 0.0001. And what would we use for x approaching 0 from the right? The same, but this time positive. 0.1, 0.01, 0.001. Okay, when we do that, here's the table that we get. So again, a conjecture. What do we think the limit as x approaches 0 from the left is of 1 over x? That seems to be negative infinity. The limit as x approaches 0 from the right would be positive infinity. Okay, so if I go back to my previous example, how did we get the limit? It seems like we just plugged it in anyway. What would happen here if we plugged in 0? It's undefined, you get 1 over 0, but so could we write something like 1 over 0, 0 minus is negative infinity, 1 over 0 plus is positive infinity. I do that all the time. But it is a notation for this. It really is saying that the limit as x approaches 0 minus from the left of 1 over x is negative infinity. As a limit, or in general, I cannot divide by 0. But if I divide 1 by something that's close to 0 and is negative, I will approach negative infinity. Okay, so that allows us then to also kind of plug it in. If we get 1 divided by 0, but something close that is negative, we will get negative infinity. Here we will get positive infinity. We'll come back to this. But so, oh yeah, if we would have looked at the graph, that makes perfect sense. On the left, we get negative infinity. And on the right, we get positive infinity. So we use the graph to come up with like an algebraic rule. Plug it in, and if you end up dividing by 0, you know you're going to get infinity, positive infinity or negative infinity. Okay, let's do another one. Use a table of values to guess the limit as x approaches 0 from the left and from the right of sine of 1 over x. Well, we just did that one, right? But with 1 over x instead. So we would use the same values for x. Negative 0.1, negative 0.01, and so on. Here's what we get. Okay. For negative 0.1, it's 0.54, negative 0.01, 0.506. So you might think maybe it's a half. We're getting closer to 0.5. Oh, no. Negative 0.001, it's negative 0.8. And then it's 0.3, then negative 0.003, then 0.35, 349, and so on. Is that getting closer to a number? No. Is it going to infinity or negative infinity? No. So here, the only thing that we could write is that the limit as x approaches 0 from the left does not exist. And similarly for the right. We're not getting closer to a number, we're not going to infinity. So something very weird is happening with that graph. Here's the graph. So a sine function always goes from 1 to negative 1. But it's normally periodic with period 2 pi, which means you cross the x-axis at like regular intervals. Every pi you cross the x-axis. What's happening with this function is that you start crossing the x-axis faster. So as you get closer and closer to the origin, you still go up and down between negative 1 and 1, but your frequency, the period, is getting smaller and smaller. This is one of those functions when you zoom in, you get exactly the same picture again. You see one blob here. So, are we getting closer to something? No. You're kind of getting seasick. Up, down, but with amplitude 1. You're going to 1, you're going down to negative 1. Going up to 1, going down to negative 1. There is no limit. So, this is the standard example, and I bet it is the only example that we know of a one-sided limit that does not exist. Okay, so is it very important for you guys on the CSET? Probably not, but there's some really weird functions out there. That limit does not exist, one-sided limits. Okay, so now that we have one-sided limits done, we can talk about two-sided limits. What does it mean, two-sided limits? The same is not true for f of x is the sine of x. Okay, so what would be the limit as x approaches 0 from the left of sine x? Well, let's graph sine x. What is the graph of sine x? It looks like this. It also has an amplitude, but if I ask you what is this, what would you do? You get on the graph to the left of 0, and you start getting closer to 0. What's your y coordinate doing? Where do you think you end up? You end up at this point, so that limit is 0. You never go from -1 to 1 up and down. No, once you're very close to it, it's not going up and down anymore. You're just going to go straight to that origin. So that limit is 0. Not a problem. And the same for the right-hand side. Okay, so it's really that 1 over x that forces that function to be so weird. Okay, two-sided limits. So what's the difference between two-sided limits and one-sided limits? Two-sided limits, you got to do both sides. Okay? So, for example, I'm going to write one out. Suppose you have a function f that's defined. Well, it's got to be defined a little bit to the left of a and to the right of a. So you got to be defined on both sides of a, but you don't need to exist at a. Finite limits, you say that the limit is L. We write this like this. No plus or minus anymore. If the values of f of x are very close to L as x approaches a. What does x approaches a mean this time? X is less than a, x is bigger than a, but x is not a. You need to check both sides. There's only one definition because there's no difference anymore between left and right. You got to do both. And you could have infinite limits. There will be two definitions there. The limit as x approaches a of f of x is positive infinity or negative infinity. So I don't even want to read all these limits definition. They're in the notes. It should be pretty clear what it means. But two-sided limit means you have to check both sides. Okay? Before we even look at an example, there seemed to be a relation between one-sided limits and two-sided limits. So if, for example, suppose that I have a function f and I tell you that the limit as x approaches 3 from the left is 5 and the limit as x approaches 3 from the right is 5. What can you tell me about the limit as x approaches 3 from the function? It should be 5, right? Whether I go from the left or the right, I think I end up at 5. What if I change this and this becomes 6? The limit as x approaches 3 from the left is 5, 3 from the right is 6. What does that mean for the limit as x approaches 3 of f of x? We would say it does not exist. I can't make a prediction. If I look on the left side, I think it should be 5. If I look on the right side, it should be 6. I can't make a good prediction. It does not exist. And that is exactly the setup of this theorem. A two-sided limit is something if and only if both one-sided limits are the same and are that something. And that something could be infinity, negative infinity, or a number. So that's why I wrote down three of them here. But the idea is the limit as x approaches a of f of x is something, if and only if the limit as x approaches a from the left of f of x is that something, and the one from the right is also that something. And in that case, the limit as x approaches a of f of x is that something. Okay, so let's see again this graph here. If we can now look at four two-sided limits, the limit as x approaches -1 of f of x. What is this limit? The limit is not 1, Vanessa. Well, what goes wrong there when you say it's 1? What did you look at? You looked at what happens when x is -1, but you should not. So you get on the graph to the left of -1. Oh, I think I end up at 3. You go to the right. Oh, I think I end up at 3 as well. My prediction it's 3. It's not what's happening, but that's my prediction. This would be a lot tougher to say cover up with a piece of paper. You would cover up with a very thin strip of paper. So let me try that like this. What you would do is, here, I delete this. What do you think is happening as x approaches -1? I think I end up at 3. Okay, the limit as x approaches 0 of f of x. That does not exist. Why does it not exist? The left is not the same as the right. The limit as x approaches 0 from the left is positive infinity. The limit as x approaches 0 from the right is 0, and they're not the same. How about the limit as x approaches 2? Does not exist for a very similar argument, right? The left is not the right. The left is 2, the right is 0. Perfect. How about the limit as x approaches 5? That one is 3. And I want to point out again that this here is not the function value, but this one happens to be the function value. Conclusion: if the limit does not exist, or it exists but it's not the function value, something weird is happening with your graph. And we have the three possible cases here. There's either a hole in your graph, you have a vertical asymptote, or you have a jump. But if your function value is the limit, like what happens when x is 5, nothing weird is going on. Smooth sailing. Okay, so let's look at this again. The limit as x approaches 0 of f of x. That one is positive infinity. The left is positive infinity, the right is positive infinity. We get infinity. How about the limit as x approaches 4? That one does not exist because the left is not the same as the right. So the left goes to negative infinity, the right goes to positive infinity. So it's not that the limit doesn't exist because it goes to infinity. No, no, no. Left and right go to different sides. Okay, so let's come up with one more. A table of values to guess the limit as x approaches 0 of sine x over x. We already, what kind of values for x do we need to use? Perfect. We gotta check both sides. So we're still going to use like plus or minus 0.0 or 0.1, plus or minus 0.01, and so on. Here's the table. What do we think the limit as x approaches 0 minus from the left is? 1 from the right. 1 conjecture. We think that the limit as x approaches 0 of sine x over x is 1. Yes, there is no calculator on the CSET, but you will never be asked to put a table out. The table is just to illustrate a concept. So this limit is 1. In the previous examples, how did we calculate that? We just plug it in, right? So what would happen here if you plug in 0 in your function? It's undefined, but what do you literally get if you plug in 0? You get the sine of 0 over 0. What is the sine of 0? 0. Ooh, that is a very big difference with that previous example. 1 over 0, we got infinite limits. But 0 over 0 could be a number. So dividing by 0 is a problem, but it seems like there's two different cases. If the numerator is 0 or not 0 seem to make a big difference. What is the graph of sine x over x? Well, if you would graph it with a calculator, you would never notice a problem. So, as x approaches 0, where should I end up? Remember, we know that the limit as x approaches 0 is 1. So that means as I come in from the left, I should end up at 1. And coming from the right, I should end up at 1. Here's how that graph looks like. It still looks a little bit like the sine. But its amplitude is going to start going smaller. But there technically is a little hole in the graph. But with a calculator, you'll never see it. It will graph right over it. But that is what that does. So if there was only a way to find that limit in a different way, then we would know there's a hole in the graph and we would be able to graph it. And that's the whole point about these limits for us. Okay? The good news is we will see a technique called L'Hopital's rule that will allow us to evaluate this limit without any problems. Okay, so we're almost done with the general description, then we go into the calculation part. So I want to end with what are the two standard cases in calculus of a limit, a two-sided limit not existing. So why would it be that the limit as x approaches 5 of f of x does not exist? Why is that? What would be the standard example that you come up with? Because the limits from the left and the right do not match. But they exist from the left and the right, they just don't match. So here is the first standard example. This is the most common one. You got yourself a piecewise defined function, and the limit as x approaches 2 from the left is not the same as 2 from the right. So the limit here as x approaches 2 does not exist. What is the limit as x approaches 2 from the left? We had to plug it into the top function. We got 3. The limit as x approaches 2 from the right was 0. We had to plug it into the top function. We notice a 0. Not the same. If this is the only example you remember, you will be absolutely fine. That is the most common way. Oh, that's a very good point. What if my function, so does that always mean that if you take a piecewise defined function, it will not exist at that point? If you have any kind of function on the left, so for example, the one that you say, what if I would make this x minus 2? Then what would be the limit on the left? Then it would still be 0. How would this function look like? Like this. So if the left and the right match, you got a limit. So in this case, the limit as x approaches 0, 2, of f of x would be 2. So you really have to do the calculations. So you can't just say, oh, it's the point where we join them, it won't work. It might work. So that is the most common example. Left and right exist, but they don't match. Well, if you're fancy, you could also look at this example. Why does this limit not exist? Because the left and the right don't exist. Not because they don't match, they just don't exist. But then again, this is a very fancy example. Okay, so we mostly are going to think of it this way, right? If the limit does not exist, it's because the left and the right are not the same. Okay, so now I need to write them down. I've seen once or twice a question like that on the CSET. This is rather abstract, the limit laws. Okay, so suppose that the limit as x approaches a of f of x is L and g of x is m, where L and m are real numbers. Then what is the limit as x approaches a of f of x plus g of x? It turns out it's L plus m. So what is this in words? The limit of a sum is the sum of the limits. Now that makes perfect sense with our word definition. What does it mean that the limit as x approaches a of f of x is L? Now f of x is getting very close to L. And g of x is getting very close to m. Well, then f of x plus g of x will get very close to L plus m. That's the limit law. One of the limit laws. And the same for subtracting, multiplying with a constant, multiplying limits, and dividing as long as you're not dividing by 0. Okay, so those are the limit laws. They make perfect sense for all practical purposes. F of a is L, g of a is m, so what is f of a plus g of a? L plus m. Okay? And you can do just about anything. Anything that you do to the function, you do to the limit. So if you take a square root of the function, you can take the square root of the limit. If you raise your function to the power 5, you can raise your limit to the power 5. Okay? So here, this last one is is actually also true if n is not just a natural number, but a square root or anything like that, but then L has to be positive, of course. Like here, this last one, what if I take the nth root of the function? I need to take the nth root of the limit. Here, I should add really, and L should be positive. But unless n is odd and so on. Okay? So let me do this in one very simple example. It's theoretical, and then we'll do a practical one. So suppose that the limit as x approaches 6 of f of x is 4, and the limit as x approaches 6 of g of x is 9. What is the limit as x approaches 6 of g of x minus 1 over f of x? Now, how did you get that it should be 2? The limit as x approaches 6 of g of x is 9, 1, and 4. So we do indeed get 2. That's officially the limit loss. How about the bottom one there? The limit as x approaches 6 of f of x plus g of x over x squared minus 1 quantity square root of that. What would this limit be? So we replace f of x by 4, g of x by 9, and x by 6. Why? What we're really using here is that the limit as x approaches 6 of x squared is 6 squared. You might wonder, why is that? Well, what is the graph of x squared? What is the graph of the function y is x squared? It's a parabola. Are there any weird points, holes, vertical asymptotes, jumps? No. So nothing weird is going to happen. And your limit, your prediction, will be what is actually happening. What is actually happening with x squared when x is 6? You get 6 squared. So that's going to be your prediction. Nothing weird is happening. Don't believe me? Just graph it and see what you would do when you take the graphical limit as x approaches 6. Oh, you're going to end up at 36. Okay? So these limit laws, I cannot prove them because our definition of limit is well, let's say pretty crappy. It's a word definition. It's not an exact definition. So you can't prove anything with such a wishy-washy definition. But what it does show is, how do you practically evaluate a limit? You plug it in. Because 99% of the time, nothing is going to go wrong. If you're not at a hole, a vertical asymptote, or a jump, it's going to be, your prediction is going to be the function value. Okay, so that we also saw that in our that's a very different thing, Vanessa. That will be what happens when there's a problem. But so here is the practical way to evaluate a limit. As long as nothing goes wrong, the limit is the function value. So hence, how do you evaluate a limit? Just plug it in there. As long as there's no problems, f of a is the answer. So when does this work fine? It works fine for just about any function you can imagine, as long as that element is in the domain of the function. It works for polynomials, rational functions, radical functions, exponential function, logarithmic function, trig functions, inverse trig functions. As long as you can plug it in, there's your answer. Here are some examples. What is a polynomial? Natural whole powers of x. All these names refer to what is happening to the variable. So what is a rational function? Your x is in the denominator, or could be in the denominator. So 2x minus 1 over x squared minus 4 is an example of a rational function. Radical function, there's square roots involved, or nth roots. Square root of x plus 1 over 1 minus x. Exponential, your x shows up as an exponent. E to the x squared minus x. Logarithmic, there's a log involved. ln of 2x minus 1. Trig, there's a sine or a cosine or a tangent involved. Inverse trig, there's an arctangent, an arccosine, and arcsine involved. All those types of functions, the first thing you do is you plug it in. And if there is no problem, then that's your answer. If there is a problem, then we need to fix that. Okay, so what is one kind of exception is the piecewise defined functions, especially at the points where you join them, because there we've seen that you could have a jump. But we've also already seen how to fix that, how to approach that. Okay, so let's do 2 examples. What is the limit as x approaches 0 of e to the x squared minus 1? What do we do? Yep, it's not 1. But you plug it in. E to the 0 squared minus 1, that's e to the negative 1. I didn't have any problems, so that's the answer. Now, I have no clue how e to the x squared minus 1 looks like, but I know there's no problem when x is 0. There's no hole, there's no jump, there's no vertical asymptote going on there. Okay, second example, the limit as x approaches 2 of that ugly thing there. All right, so plug it in. We get 2 times 2 squared minus 3 times 2 plus 1 over 2 cubed plus 4 squared. And then we calculate that. 2 times 2 squared is 2 times 4 is 8, minus 6 is 2 plus 1 is 3. 8 plus 4 is 12 squared. That's a quarter, so that is indeed 1/2. There's your answer. I do maybe want to do one little example here. It's a technicality, but what would be the limit as x approaches 5 of the square root of 3 minus x? What would you say this limit is? Okay, if you tell me it does not exist, I'll be happy. But basically, this does not make sense. It does not make sense for me to ask the limit as x approaches 5. Why? From our definition, the function should exist around 5. What is the domain of this function? Uh, 3 minus x needs to be positive. So x is less than or equal to 3. This is defined in negative infinity to 3. So this does not exist around x is 5. It's okay that it doesn't exist at 5, but we should exist a little bit to the left of 5 and to the right of 5. And that is absolutely not true. So the graph of that function might look something like this if x is 3. Right? And you're asking, what do you think the function value is at 5? That doesn't make any sense. I cannot make any prediction about that because the function doesn't exist around 5. Okay, so just a technicality, you might wonder, is it a problem if you get a negative number? Technically, no, because that means you shouldn't even ask that question. If the squared, it means it doesn't exist at that number. So if you do want to write down the limit does not exist or the limit does not make sense, either way, you're fine. Okay? So let's do an example with a piecewise defined function. So, and let me to make that point clearer, let me delete that equal sign. All right, here's my function. What is the limit as x approaches 3 of that function? What do we want to do? We want to plug in 3. Oh, that's a little too fast there, Jerome. What is the only x value that you may have a problem here? The only x is where we join them. There could be a problem at x is 2. But the limit as x approaches 3 is not a problem because it is really the same as the limit as x approaches 3 of x minus 3 squared. And what is that limit? I think I saw it there in the answers. You plug it in. So why were we able to plug it in? Since 3 is strictly bigger than 2, we have no problem. We use the bottom formula. Similarly, the limit as x approaches 0 we just plug in 0 in the top one and we get negative 3. Not a problem. The limit as x approaches 2, oh, there we got to be careful. So that's one way you need to recognize it's not just about plugging in 2. At the point, you have to do both sides. So we didn't have to do that for these guys because there was no problem there. We're not putting them together. At x is 2, we know there might be a problem. So we calculate the limit as x approaches 2 from the left. What is the limit as x approaches 2 from the left? We plug in 2 still, but in the top formula. So sometimes my students go like, oh, wait a minute. We cannot plug in 2 into the top formula. We're not really plugging in 2. As x approaches 2 from the left, is x bigger than 2 or less than 2? X is less than 2. That's why we use the top formula. So we get 8 minus 3 is 5. What is the limit as x approaches 2 from the right? That would be the bottom formula, because as x approaches 2 from the right, x is bigger than 2. And so we get 2 minus 3 squared, which is 1. We have not the same. So now we can say that this does not exist. So with questions, with exercise like that, you need to be aware, hey, there could be a problem where we put them together. All the other points will not be a problem. We just got to figure out which formula we need to use. Okay, so that's it. We did limits, we plug it in, and we know what to watch out for. So, what is the uh, if what if this was the function, the original one? That will not make a single difference when x is 2 for the limit as x approaches 2 because we don't care what that does. It's a prediction we're making. We're making a prediction that we think that you can't define what f of x is. So basically, how does the graph of f look like? Very abstractly, as x approaches 2. From the left, I should be ending up at the limit as x approaches 2 from the left was 5. So what does that mean? I got something here and I'm going to end up at 5. And from the right, it was 1. So I end up somewhere here 1. It doesn't matter where you put a solid dot on this line or where you don't put a solid dot. Whether there is a solid dot or no solid dot, and it doesn't matter where it is, those two limits will still be 5 and 1, and the two-sided limit will not exist. Okay, so then you might wonder, well, when is there a problem then? Well, what is about the only problem when you plug in a number in a function and that you could? So we're not talking about a square root that has a negative number in there. That's not in the domain. So the only time that you have a problem is when you divide by 0. That's the only problem you could ever encounter. But we've already seen, what does that mean if you end up dividing by 0? Your number a is not in the domain of your function. Right? So what does that mean? Well, you got unlucky. It's one of those 1% of the cases that something goes wrong. So you're going to have to do something different to evaluate that limit, if it exists. Right? So dividing by 0 leads to two different cases, as we've seen in examples already. And each one has its own different method of solving. Namely, you could have 0 over 0, like sine x over x, or not 0 over 0. So we're going to start with 0 over 0. Later on, we call that an indeterminate form. Why is that? It could be anything. We just don't know yet what it is. It's indeterminate at this moment. So a limit of the form 0 over 0 could be a number, could be infinity, or might not exist. You just don't know. Well, later on, we are now going to take it to the hospital. We describe one method that might work, factoring, and another method will be in the L'Hopital's rule. But even though L'Hopital's rule is very powerful, some of the things we're going to do now turn out to be easier than using L'Hopital's rule. So it's still a very useful method. Okay, so before I need to mention one theorem, you don't need to memorize it, but it's really the justification on how we evaluate certain limits in determinate forms. Namely, suppose that you have a function g of x and that the limit as x approaches a of g of x exists. Finite or infinite, it exists. And that you have a function that f of x that's equal to g of x, except when x is a, possibly. Then the limit as x goes to a of f of x is the same as the limit as x approaches a of g of x. Why does that make sense? Well, what is the one value of x that we don't care about if we consider the limit as x approaching a when x is a? So If I delete that x as a, then f of x is exactly the same as g of x. So whatever prediction you're making for g, you will make exactly the same prediction for f, because your decision is based on values when x is not a. Mhm. So practically, if you have to calculate a limit of a quotient, and if the numerator and the denominator have a factor in common, you can always, always cancel those factors. Whether that factor is zero or not doesn't make a difference. You can always cancel the same two factors. Okay, so let's see what that means. So suppose you have a limit of the form 0 over 0. So what does that mean? F of x is a fraction, and when you plug in a, you get a 0 in the numerator and a 0 in the denominator. Now, if you have a polynomial and you plug in 2 and you get 0, what does that mean? What should be a factor of a polynomial when you plug in 2 and you end up with 0? So that's maybe a little more general function. So suppose we have a function f of x, and we know that f of 2 is 0. Then f of x seemingly should be something x minus 2 times something else. That was called the factor theorem, right? Clearly, if it's x minus 2 times something, you would have, when you plug in x is 2 is 0. But so that's what we expect. If I plug in 2, x, and I get 0, x minus 2 should be a factor. Well, at least it's true for polynomials. So here, I plug in x as a, and I get a 0 in the numerator and a 0 in the denominator. So I expect that the numerator and the denominator both contain the factor x minus a. Huh. But then by this theorem, we can just cancel out those two factors. And so we end up with a new limit. How on earth could that help us? With the big picture is that if we believe that these limits are useful for graphing, what would it mean that the limit of a function is 0 over 0 and then turns out to be 5? Well, first of all, it means that your function didn't exist at a, but that the limit is 5, so that means there's a hole in the graph. The x-coordinate of the hole is the number a, and the y-coordinate of the hole is that number L. This theorem is not about defining continuous functions. We're kind of evaluating limits already based on knowing what continuous means, and I'm going around a little bit in circles, but that's because we don't have a nice definition of a limit. Okay? So why can't we plug it in? Officially, that's the definition of continuity, but we'll get there later. Okay, so right now, this is just a very practical way of evaluating limits. If you can cancel out the same thing in numerator and denominator always, and you get a new limit. Okay? So let's have a look at the limit as x approaches 1 of x squared minus 1 over x minus 1. What is the first thing we should do? The first thing I always do when evaluating limits, I do not factor. I first plug it in. For example, what would you do if there was the limit as x approaches 2? plug in 2. There might not be a need to factor. Here I plug in 1. And I have a problem. I'm dividing by 0, and the numerator is also 0. If there is no problem, don't create one. So we don't need to factor to find that limit. We only factor if we have a problem. So we have a problem, so now we factor. When we plug in x is 1 and we get 0, what do you expect to be a factor? X minus 1. Well, that's already clearly in the denominator, right? So how about the numerator? X minus 1 is a factor. What's the other one? X plus 1. Now we can use that theorem or the practical application. You can cancel out always common factors. And that has nothing to do with whether the limit is 1 or not 1. So we end up with the limit as x approaches 1 of a new function. We're not done yet. We just came up with a new limit. And how do you calculate this new limit? You start all over again. The first thing you do is you plug it in. This time we have no problem. We get 2. Right? So that begs the question, if I call this function f of x and the function x plus 1 equal to g of x, what is the difference between f of x and g of x? The difference is at the domain. What is the domain of g of x? It's all real numbers. So let me graph g of x. That is just a line. So what is my graph of f of x? The same one, but there's a hole. Where's the hole? The hole is when x is 1. So what is the coordinates of that hole? Well, look over here. When x is 1, what is this point? The coordinate is 2. 1 plus 1. So the coordinates of that point, that hole, are 1 and 2. So if you would graph this with a computer, you will never see the difference. It's going to graph right over it. Okay? If you have a limit of the form that is 0 over 0 and it turns out to be a number, then there's a hole in the graph. Now you might wonder, why on earth would anybody want to work with a function like this? Just work with x plus 1. And that's a very valid argument. However, what happens if we did our example for f of x is sine x over x? The limit as x approaches 0. What happens when we plug in 0? We get 0 over 0. So when you plug in x is 0 and you get 0, what do you expect to be a factor? If we plug in 1 and we get 0, what should be a factor? x minus 1. If you plug in 0 and you get 0, what should be a factor? X. But here, we cannot factor an x out of sine x. See? So, yes, the illustration that I need to give you is examples where we can factor out. And then, of course, you might wonder, why on earth would you do that? But there are a lot of examples where we cannot factor out, but it's the same principle then. You're going to end up with a hole in the graph. Okay? So that's the difference between these two functions. So let's do another one. The limit as x approaches 3 of that function. What do? Plug it in. Okay, so we get 3 squared minus 3 times 3 over 2 times 3 squared minus 5 times 3 minus 3. Okay, now let's say that we had 0 over 5. Is that a problem, 0 over 5? No, 0 over 5 is just 0. So that would not be a problem. But here it's, of course, it is a problem. It's 0 over 0. Okay, so we try our factoring method. What do we expect to be a factor? X minus 3. Now that's easy to see in the numerator. What do you do to factor the numerator? It's x minus 3 times x. You factor out an x, right? But the denominator is a little harder. But if you know that x minus 3 should be a factor, then it's very easy to come up with the second factor. What should be the second factor? In order to get 2x squared, that needs to be 2x. In order to have negative 3, there's got to be a 1. And now we can quickly check. X squared plus x minus 6x is minus 5x. Correct. Now we can cancel our x minus 3. And typical for these indeterminates, we come up with a new limit. X over 2x plus 1. We start all over again. We plug it in. We plug it in. There's no problem this time. So we get, plus 1. We get 3 over 7. So there's a hole in the graph of this function at x is 3. The y-coordinate is 3 over 7. What is the difference between this function and this function? At x is 3. This guy has a hole at x is 3. This guy does not have a hole at negative 3. At 3. Okay? So that's just to illustrate this technique. All right? Here's a different example. And this is an example where L'Hopital's rule might get you, might be a little bit harder. Okay? So the limit as x approaches negative 1 of the square root of x plus 2 minus 1 over x plus 1. What do? We plug it in. Sorry, not x plus 1. Negative 1 plus 1. We immediately see the denominator is 0. That's a problem. Numerator square root of 1 is 1. Minus 1, we get 0 as well. So what do we expect to be a factor? X plus 1. That's right there in the denominator. But the numerator, how on earth am I going to get an x plus 1 in there? So there's a little trick. Why is it so hard? to see the x plus 1 in the numerator because of that square root. There is a standard technique that gets rid of the square root. It is not squaring both sides. It is multiplying by the conjugate. Just the same you would get rid of a square root in the denominator if you didn't like it. So we multiply top and bottom by the conjugate of that square root. So the conjugate is plus 1. Change the sign on one of them. And work it out. So let me do one extra step. That's the square root of x plus 2 minus 1 times the square root of x plus 2 plus 1 over x plus 1 times square root of x plus 2 plus 1. And we're going to start foiling. Which one do we not need to FOIL? The denominator. Why? Well, remember why we did all this. We wanted to get the factor x plus 1 in there. We got it in the denominator, so there's no reason to change that. It's the numerator that we want to deal with. Do you see a slightly faster way to maybe work out the numerator? It's a difference of squares. A minus b times a plus b. That's a squared minus b squared. But if you just FOIL it, it would work as well. So what do we get? It's the limit as x approaches negative 1 of square root of x plus 2 squared minus 1 squared over that denominator. What does that denominator become? A numerator become? It becomes exactly x plus 1. We get x plus 2 minus 1, which is x plus 1. We got our x plus 1 in that numerator. So now we can cancel out. And we got a new limit. 1 over square root of x plus 2 plus 1. With new limit, we start all over again, plug it in. 1 over negative 1 plus 2 squared plus 1, which is indeed 1/2. L'Hopital's rule works reasonably okay as well, but this is definitely a nice example where factoring comes in a little handy. So roughly speaking, instead of working with this function, you could also work with this function here. Big difference, the original function does not exist at negative 1. This guy does. Okay, I think we got one more example. Ooh. The limit as x approaches 1 of that ugly thing. We start by plugging it in. 1 over 1 plus 1 minus 1/2 over 1 minus 1. We get 1/2 minus 1/2 is 0. 1 minus 1 is 0. What do we expect to be a factor? X minus 1. So how could I get that factor x minus 1 in that numerator there? You should always first identify the problem before you try to solve it. So this has nothing to do with multiplying by conjugates. Last time, why did we not see that factor x minus 1? Because there was the square root in it. Why do you not see the factor x minus 1 in the numerator here? So somewhere there should be an x minus 1 in here. Why do you not see it? That's probably the answer to the question, but to the exercise, but why do you not see an x minus 1 in there? Because there's all these fractions involved. So let's first simplify the fraction before we try to do anything fancy to get that in there. So I'm not touching x minus 1 there. Common denominator is 2 times x plus 1. That means 1 over x plus 1 I need to multiply by 2. The 1/2 is multiplied by x plus 1. Subtract, don't forget parentheses. And now we'll simplify everything. So that numerator, we get 2 minus x minus 1, which is 1 minus x. And finally, I'm still got a little bit of extra work to do. I need to simplify. So we're dividing. Where does this x minus 1 go? Does that go in the numerator or in the denominator of this guy? The denominator, right? It's dividing by 1. So multiply by the reciprocal. We get 1 minus x over 2 times x plus 1, x minus 1. So there seemed to be one little, very little problem left. I was supposed to get an x minus 1 in the numerator, so I can factor out a negative 1 in the numerator and indeed have my factor there. So now we cancel out our common factor. Sorry, that's the wrong one. We are left with negative 1 over 2 times x plus 1. So we plug it in. We got our new limit. Negative 1 over 2 times 1 plus 1. And we end up with negative a quarter. Okay, so those are the standard examples of what to do with 0 over 0. What's the next problem that we had? Non-zero over 0. Based on the graph, we kind of know already what's going to happen. What does that do to your graph if you have something non-zero over 0? There's a vertical asymptote. So what that means is that it's not a hole. Like the graph of 1 over x, it has a vertical asymptote. So what does that mean in terms of limits? One-sided limits of the form non-zero over 0 will always be some type of infinity. Always. But it's important here that it's one-sided. Because what could go wrong with two-sided limits? One side could go to negative infinity, the other side to infinity, and then the limit itself does not exist. But one-sided limits of that form will always be plus or minus infinity. The only thing we got to do is figure out if it's positive infinity or negative infinity. So for two-sided limits, you would have to check both sides. So recall this graph here of 1 over x. when we did that, we had two limits. The limit as x approaches 0 from the left is negative infinity. The 0 from the right is infinity. So based on our approach of how we would evaluate limits, plug it in, I write things like 1 over 0 minus is negative infinity, 1 over 0 plus is positive infinity. But that's just the notation for this. I know I can't divide by 0, but 1 over something that's close to 0 and negative, that will give me negative infinity as a limit. Okay, so how can we now, without a calculator, deal with these type of limits? Well, so first of all, you should factor the denominator. Basically, there's a part of the denominator that gave you 0, a factor x minus a, right? Write all the rest on the other side. So split it. So that means you're going to get 1 over 0 in one of these guys, and then just figure out if it's 1 over 0 plus or 1 over 0 minus. And then use the standard sign rules to decide if the one-sided limit is infinity or negative infinity. With that, I mean, what do you think 2 times positive infinity is? Infinity. 2 times negative infinity? Negative infinity. Negative 3 times positive infinity? Three times negative, negative 3 times positive infinity. What should that be? Negative infinity. And negative 3 times negative infinity. That should be positive infinity. So standard sign rules that positive times negative is negative, positive times positive is positive, negative times negative is positive. So if r is bigger than 0, positive times positive infinity is positive infinity, positive times negative infinity is negative infinity. And similarly for negative. You cannot multiply infinity by 0. That we don't know what that is. That could be anything. Okay, so let's do a standard example. The limit as x approaches 1 of 3 over 1 minus x. The first thing you do is you plug in 1. You get 3 over 1 minus 1. We get 3 over 0. Uh-oh. So we know the one-sided limits will be some type of infinity. The two-sided one we don't know. So let me start with the one-sided limit, the limit as x approaches 1 from the right. There's not really much reason to rewrite this. It's still 3 over 0 when I plug it in. I just want to know if I plug in, will this be 0 plus or 0 minus? Well, as x approaches 1 from the right, what does that mean? Is x then bigger than 1 or less than 1? X is bigger than 1. If x is bigger than 1, then what can you tell me about 1 minus x? Will that be bigger than 0 or smaller than 0? That will be negative. If you have a hard time seeing that, well, give me something that is a little bit bigger than 1. 3 is quite far, like 1.1. Well, what is 1 minus 1.1? Negative 0.1. Ah, that's negative. Okay, so what does that mean? I now know that this should be 0 minus. So what this really means is 3 times 1 over 0 minus. Okay? 1 over 0 minus as a limit, what is that? One over 0, I know it doesn't exist, but as a limit, since we're dividing by something negative, is negative infinity. And then, what is 3 times negative infinity? Negative infinity. Okay, so the right side limit of x approaching 1 of 3 over 1 minus x is negative infinity. You can do something very similar for the left. I know it's 3 over 0. As x approaches 1 from the left, are we less than 1 or bigger than 1? X is less than 1. So what does that mean for 1 minus x? It's positive. 1 minus 0.99 is indeed 0.101, which is positive. We don't even have to go that far, of course. You could just do this. But the point is you got to get reasonably close at 0.1, which is positive. So now I know that this is 0 plus. It really is 3 times 1 over 0 plus, which is 3 times a positive infinity, which is positive infinity. Okay, so what does that now finally tell us about the limit as x approaches 1 of 3 over 1 minus x? Does not exist. But make sure to understand it's not because we're dividing by 0 that it does not exist. It's because we get two different answers for left and right. What does that mean for the graph of f? There's a vertical asymptote at x is equal to 1. And on the left side, what is happening to the function on the left side of 1? It's going to positive infinity. And on the right side of 1, it's going to negative infinity. That's how our function should look like. It helps us graph. Okay, let's do two more like this. The limit as x approaches 2 of 1 minus 5x over x minus 2 squared. All right, so we plug it in. 1 minus 5 times 2 over x minus 2 squared. 2 minus 2 squared, what do we get? We get 1 minus 10 is negative 9 over 0. Okay, we should check both sides. So let's start with the right-hand side. I know when I plug in 0, 2, I'm going to get negative 9 over 0. I just want to know if it's 0 plus or 0 minus. Well, as x approaches 2 from the right, is x then bigger than 2 or less than 2? What does that mean for x minus 2 squared then? Is that going to be positive or negative? Positive. We could plug in 2.1 if needed. Okay, so it's plus. So what do we get? Negative 9 times 1 over 0 plus was negative and positive infinity, but times negative 9 will give us negative infinity. But you're absolutely right. What happens if I pick the limit as x approaches 2 from the left? I get exactly the same answer, negative 9 over 0. X approaches 2 from the left, means x is less than 2, but still we know that x minus 2 squared will be positive because we're squaring. For example, x is 1.9. 1.9 minus 2 squared is indeed a negative number squared, and that's still positive. So here we still have 0 plus. That means we still have negative 9 times positive infinity. We still have negative infinity. So, based on this, what is the limit as x approaches 2, the two-sided limit? We can now confidently say that that limit is negative infinity because we had twice negative infinity. All right? So, what does that mean for the graph of the function? There's a vertical asymptote at x is 2. And what is my function doing? It is going to negative infinity both sides. That's how it's going to look like. Okay? If you had a calculator, do you need to do all this stuff? Of course not. Then, the moment you do this, what you do with a calculator is, let me just plug in two numbers very close to 2. Plug in 2.1 in this whole thing and see if you get a positive or a negative number. You're going to get a negative number. Plug in something less than 2, 1.9, the whole thing, you're going to get a negative number. That tells you these limits. But we can't by hand plug in 1.9 in this. It's going to take us forever to figure this out. So that's the illustration of the last example that we will do. X squared minus 4 over x squared minus 7x plus 12. The limit as x approaches 3 from the left. Okay. What's the first thing we do? Plug it in. We get now 3 squared minus 4 over 3 squared minus 7 times 3 plus 12. 9 minus 4 is 5 over 9 plus the 20 over 0. So we know what will the answer be? Some type of infinity, but we don't know which one. So if you had a calculator, how could you figure this out? Plug in 2.9 in the whole thing. If you get a positive answer, then the answer will be positive infinity. If you get a negative answer, it's negative infinity. But if we don't have a calculator, then we got to figure out ourselves basically, if you stay close to 3, will this thing be positive or negative? Huh? For that, what we do is, what is making us get a 0 in the denominator? Why is that? What should be a factor? There should be an x minus 3 in there. What's the other factor? X minus 4. We don't need to factor the numerator. The numerator is not giving us a problem. Because the numerator, if you plug in 3, you get 5. So I don't need to factor the numerator. I want to figure out what is giving me 0. We now need to rewrite this as what is giving me 0? Only the x minus 3. What is not giving me any trouble is the rest. So, let me write this. Now, plug in 3 again. What do you get now when you plug in 3? So, plug in 3 in here, plug in 3 in here. I'll do the easy one. The last one gives you 1 over 0. What does the first one give us? 9 minus 4 over 3 minus 4. This is negative 5. So we get negative 5 times 1 over 0. Now I can figure out what type of 0 that is. X is approaching 3 from the left. Is x less than 3 or bigger than 3 then? X is less than 3. So will x minus 3 be positive or negative? If you need to do a little example here, x is 2.9. 2.9 minus 3 is negative 0.1, which is negative. So that means it's 0 minus. 1 over 0 minus is negative infinity. Negative 5 times negative infinity is positive infinity. So now we know that that limit is positive infinity. If x is close to 3 from the left, this whole thing should be positive. If I had a calculator, it would have been easy. By hand, you could, of course, risking just let me plug in 2 and see if it works. But the kind of exercises I give, I make sure that you get 0 when you plug in 2. So then that wouldn't help you. Okay, for everybody? So in these more complicated exercises, you factor the denominator to figure out what exactly is causing my 0 and what is not giving me any trouble. Now I plug it in, I get negative 5. Yes, if this was the same as with 0 over 0, I plug in 3 in my denominator and I get 0. That means x minus 3 should be a factor. Oh yeah, the other one is x minus 4. So all this work just so that I could figure out if this thing is positive or negative. It's positive. Okay, one last technique, which is not used very often, is what we call the squeeze theorem. What is the squeeze theorem? Okay, suppose that we have 3 functions, an f, a g, and an h, and you know that f is less than g is less than h. And suppose somehow that you also know that the limit as x approaches a of f of x is a number L, and that is that the same as the limit as x approaches a of h of x. Then the limit as x approaches a of g of x must be the same. So what is that basically saying? If f and h are getting closer to, let's say, 5, and g is in between, then g has no choice but to go to 5 as well. G is squeezed. Okay, so when do we practically ever use that? It mostly means that you want to calculate the limit as x approaches a of f of x, but it doesn't exist. Why does it not exist? Because typically there's a part of it, a piece of it that doesn't have a limit. But hopefully it can be bounded, like a sine function or a cosine function. So let's do this in one example. It's already a little bit advanced because we only know of one function that doesn't have a limit, because where the limit doesn't exist, and that's the sine of 1 over x. So what would I want to do to calculate this limit? I want to plug in 0, right? So I would get 0 times the sine of 1 over 0. But the problem is that this does not exist, even as a limit. So it's not just I'm dividing by 0, it just doesn't do anything when I get close to 0. So what do? We try the squeeze theory. But we need to come up with those bounds. So here, the part that's given us trouble is the sine of 1 over x. Can we somehow find inequalities on that? Well, it's a sine. What is the biggest that the sine of anything can ever be? 1. What is the smallest that a sine can ever be? It could go all the way to -1. Okay. I want to know something about x sine 1 over x, so I multiply everything by x. Oh, I gotta be careful. If you multiply inequalities by a number, what do you have to be careful about? The positive or negative, right? But it's not a problem. X is approaching 0 plus, so x is bigger than 0. So if I multiply everything by x, I get -x is less than or equal to x sine 1 over x is less than or equal to x. That is the perfect setup for a squeeze theorem. The function I want to know something about is in between two other functions. Next step, you need to calculate the limit of those two other functions and hope that they are the same. What is the limit as x approaches 0 from the right of x? We plug it in. What is the limit as x approaches 0 from the right of -x? Also 0. They are the same. So what does that mean? So the limit as x approaches 0 of the function should be exactly the same. So let me maybe use some colors or where these zeros come from. We get that this limit is 0, this one is 0, so that one must be 0 as well. You might wonder, I have a hard time understanding what that function looks like, because wasn't the sign the wording of the definition of limits? No, I'm pretty sure that you don't need to know that you need to be able to calculate limits and see them on a graph, but not the definition. Everybody's word definition of limit is different, so that wouldn't really work too well. But remember that graph sine of 1 over x? It was going up and down, and that's why the limit doesn't exist. So how about this guy then? Well, here's how it looks like. X sine 1 over x. It's still violently going up and down faster and faster. But what is happening to the amplitude of this going up and down? That amplitude, you're not going between 1 and -1. You're going up, but each time less and less. And that's why that limit is still 0. You can clearly see the functions y is x and y is negative x in here. Here's the function y is x. And here is the function y is negative x. That should, of course, go through here. There is no vertical asymptote at 0. There's a limit. There is a hole here, but it's very weird form. So, not too bad. The squeeze theorem is used very few times. It's very rare. So, if you want to skip this example, you'll probably be absolutely fine. But it's just, there's another technique there. Okay, so what is very important is that you remember how we evaluate limits. Plug it in. If there's no problem, there's your answer. Piecewise defined functions are a little different. And what to do when you got 0 over 0, what to do when you got non-zero over 0. I am going to skip the formal definition of a limit. I noticed that they require you to know this, but this will really take me away very far. So instead, I'm going to talk about continuity. What is the actual definition of continuity? So you have continuity at a point and continuity on an interval. Continuity intuitively means without interruption. So what is like a calculus definition, practical definition of what does it mean for a function to be continuous? You can graph it and you never have to take the pencil off the paper. There are no holes in your graph, there are no jumps in your graph, and there are no vertical asymptotes in your graph. Here is the mathematical definition. A function f of x is continuous at a point a, or is continuous at x is a, if the limit as x approaches a of f of x is f of a. You might think, oh, that means one thing. No. That's really 3 conditions. First of all, f of a must exist. So that means a must be in the domain of your function. If you do not exist at a point, you cannot be continuous at that point. Okay? The second one means that the limit as x approaches a must exist. We've seen examples where it doesn't exist if the left and the right don't match up. And thirdly, even if f of a is defined and the limit exists, they got to be the same. And here we really mean with the limit exists, it must be a real number, not infinity. Okay, so 3 conditions. So, in math, we have some special words. Instead of saying, what does it mean to be not continuous? We use the word discontinuous. So discontinuous just means not continuous. But what is what is used quite often? A point A is a point of discontinuity, is a discontinuity if you're not continuous there. Probably why there's a lot more points where you are continuous than you're not continuous. Right? And then what are the 3 most common reasons why a function is discontinuous, not continuous at A? Well, first of all, It could be that the limit exists, but is not equal to f of a, or that f of a doesn't even exist. What does that mean? You have a hole in the graph. And we call that type of discontinuity a removable discontinuity. Why? Here's a graph. Right? And it has nothing to do whether this is a solid dot or not. Okay? The limit exists, but it's not the function value. So if I would have this type of graph, that would be the same thing. Now, why do we call that a removable discontinuity? If you could change one point on the graph of f of a, could you make this guy continuous? What would you have to do to make this function continuous? Remove the hole. How could I remove the hole? Just color it. And now it's continuous. So by just changing the definition of your function at one point, by defining f to be L, so if this limit is L, if we define f of a to be L, then f is continuous at x is a. You can make the function continuous, so it's a removable discontinuity. If you make a function equal to its limit, then it's got to be continuous at it. Okay, so that's the first type. The limit exists, but it's not the function value. Okay, the second problem that you could have is that the limit doesn't exist. Why? Because both limits, one-sided limit exists, but they're not the same. What does that mean? There's a jump in the graph. The limit on the left is -1, the limit on the right is 5. You jump from -1 to 5. We call that appropriately a jump discontinuity. Here's a graph. You can never make that continuous. You could say, I'm going to color this guy, but it's still discontinuous. No matter what you change here on that one point, you can't make it continuous. Okay, so then there's the third part, is that one of the one-sided limits, or maybe both, are infinite. Then we have a vertical asymptote. We call that an infinite discontinuity. Okay, so how can we, without graphing, realize all of that? Well, we got to find limits. So if I quickly go back, if the limit of your function exists, but it's not the function value, it's removable. If the limits on the left and on the right are numbers, but they're not the same, you got a jump discontinuity. If one of the limits is infinite, you got yourself a vertical asymptote, so you have an infinite discontinuity. So by just trying to find a limit, you can figure out what type of discontinuity you have. Okay, that is continuity at a point. What is continuity over an interval? You just say that you got to be continuous at every point in the interval. No big deal. Okay, if you would happen to have an interval that has an endpoint in it, you technically need to use a one-sided limit. No big deal. Okay. Now, how did we calculate limits? We just plugged it in. And if we didn't have any problems, like dividing by 0, then that was our answer. Conclusion: the limit as x approaches a of f of x is f of a. So what does that practically mean? Most of the functions that you know, and I even would dare to say all the functions that you know, are continuous on their domain. If you can plug in a and you get a number, then that is the limit and you will be continuous at that. So all the functions that we mentioned in limits, they are all continuous in their domain. What's the only exception? Piecewise defined functions. There you have to be careful at the points where you go piece them together. But any other function, asking where you are continuous is really the same as asking what's your domain. And we will see that in some examples. Okay, so here's a bunch of exercises. I give you a function and you need to figure out where is the function continuous, where is it not continuous, and could you tell me what type of discontinuity you have? Let's look at the function 2x to the fourth minus 5x plus 1. What is the domain of this function? Domain of f is all real numbers. Conclusion: you're continuous everywhere. So f is continuous on the interval negative infinity to infinity. People also call this everywhere. So what does that mean? F does not have any discontinuities. So no holes, no jumps, no vertical asymptotes. Okay, so that's pretty neat. Okay, let's look here. The function f of x is 4 minus x squared if x is less than or equal to 3, 4x minus 7 if x is bigger than 3. What is the domain of this function? The way it's written, the domain is still all real numbers. But basically, if I look at 4 minus x squared, what is the domain of purely 4 minus x squared by itself? So not in this exercise, but if I would just tell you, hey, the function 4 minus x squared, what is its domain? It's all real numbers. So 4 minus x squared is continuous everywhere. So that means 4 minus x squared is not a problem. If you graph 4 minus x squared, there's no holes, no jumps, no vertical asymptotes. What is the domain of 4x minus 7? It's also all real numbers. So 4x minus 7 is continuous everywhere. But now when we do that for f of x, there could be a problem. Where could there be a problem? So f of x is continuous everywhere. I'm going to write except possibly at x is 3. That's the only problem that you could ever have. Is there a problem? Well, calculate the limit. So calculate the limit as x approaches 3 of f of x. What is the limit as x approaches 3 of 3 from the left of f of x? X approaches 3 from the left, we need to use the top formula, we get negative 5. The limit as x approaches 3 from the right, what do we need to use there? The bottom one, 4 times 3 minus 7, which is 5. Not the same. So yes, the limit doesn't exist, but what type of discontinuity is it now? Hence, x is equal to 3 is a jump discontinuity. If both one-sided limits are numbers, but they're not the same, it's a jump discontinuity. Okay? You have to be very careful. Right? So what happens if I would change this to 7 minus 4x? Then they are the same, so what would, as x is equal to 3, would now be continuous. Now let me make one more change. What if I change that to 7 minus 4x and change this to x is less than 3? What happens now? The limits are the same, but it is not continuous. Does this new function exist at 3? No. So what happens if the limit exists, but the function does not? What kind of discontinuity is that? The limit exists, but it's not continuous. Yes, but it's one of the 3 types of a discontinuity then. It's a removable. So what is the graph? There's a very silly difference between them. So it was the limit, I forgot, as x approaches 3, and we got 5. So in the first case, I get a function that looks like this. And then maybe a parabola. This function is continuous at 3, right? In the second case, this is my function. That function is not continuous at 3. It's a removable discontinuity. So I'm making very little minor changes there, but the point is you have to keep checking. So in this exercise, it makes a very big difference if it's less than or equal to 3 or strictly less than 3. So I'm going to erase that now. But this function, as is given, is not continuous at 3, and we have a jump discontinuity. How about the function x squared minus 1 over x squared minus x? Before you do anything, find the domain. What is the domain of this function? The denominator cannot be 0. So we figure out the bad points. When is it equal to 0? We factor, so we get x is 0 or x is 1. What does that mean? We now know that f is continuous on, or what is the domain of f? Negative infinity to 0, union 0 to 1, union 1 to infinity. So now we know for sure already that f is continuous on these three intervals. Continuity is a property of intervals. We also know that x is equal to 0 and x is equal to 1 are discontinuities. The function does not exist at these points. It's got to be discontinuous at it. What we don't know is what type of discontinuity we have. Okay, how can we figure out practically without graphing with limits how to do that? We calculate limits. So which type? Limits is the answer. Now remember that the exercise is not find the limit. The exercise is what type of discontinuity is it? So the moment you know the answer, you're good to go. So let me write, what is the limit as x approaches 0 of x squared minus 1 over x squared minus x? What's the first thing we do? You plug it in. What do we get? Negative 1 over 0. The question is not, what is the limit? We were finding or trying to find the limit to answer what type of discontinuity we have. Can you now already tell me which kind of continuity we have? We know that x is equal to 0 is a vertical asymptote. So x is equal to 0 is an infinite discontinuity. I'm going to write it like this. Okay, I didn't find a limit. In fact, the limit does not exist. The one-sided one, the one on the left, I'm making it up, goes to negative infinity. The one on the right goes to positive infinity. But that was not the question. Okay, so we now know that x is 0 is an infinite discontinuity. Okay, we do something similar for the other one. The limit as x goes to 1 of x squared minus 1 over x minus x squared minus x. What do we do? Plug it in. We get 0 over 0. What does that mean, 0 over 0? So I want to make sure that you understand at this point could be anything. You still don't know if we have an infinite discontinuity or not. So how do we deal with 0 over 0, L'Hopital's rule, or factor? 1x minus 1 should be a factor. The numerator, the other factor is x plus 1. X minus 1 should be a factor. The numerator, the other factor is x. Cancel out our x minus 1. We get x plus 1 over 1 over x. 1 plus 1 over 1, which is 2. Now we know what it is. what kind of discontinuity is this? This here is a number. So now we can decide that x is equal to 1 is a removable discontinuity. There's a hole in the graph. You might say, so couldn't we have done that immediately once we find 0 over 0? No, that limit could have been infinity. And then it would have been a vertical asymptote, an infinite discontinuity. The definition of removable discontinuity is that the limit must be a number, but not equal to the function value. There is no function value at 1, so we just need to have a limit that is a number. If the limit is infinite, we had a vertical asymptote. Could it be that you get the limit infinity? Sure. If you change this here to, what if there would have been an extra factor, x minus 1 left in the denominator? It would have been a vertical asymptote and an infinite discontinuity. Okay? So mathematically, how do you classify discontinuity? Sure, yes, a jump is that this here. Both one-sided limits must be different. That is a jump. Here, both sides will be the same. Both sides will be 2. So there's no jump there, but there's a hole in this case. Okay, so whenever I ask this to my students and I ask them show your work, that means show me your limits. Calculate first the domain that tells you where the discontinuities are, and then how do you figure out which one is what? By calculating a limit. Okay, so I do want to point out a whole bunch of theorems for continuous functions, but they are really coming from the limit laws. If f and g are continuous at a point A, then f plus g, f minus g, a constant times f times g, and f over g will also be continuous. Why? Because of the limit laws. As long as you're not dividing by 0. If g is continuous at A and f is continuous at g of A, then f after g is also continuous at A. That one takes a little bit more work to prove. Okay, so, but you're roughly speaking, whatever you can do with limits, you can do with continuous functions. If you can add limits, you can add continuous functions. Okay, the last result that we need for tonight is called the intermediate value theorem. It's a theoretical result, but it makes perfect sense when we think about it. Also, let me state the intermediate value theorem. The intermediate value theorem is, let f of x be continuous on a closed and bounded interval AB. If z is any real number between f of A and f of B, then somewhere there exists a number c in the interval AB such that f of c is equal to z. Let's see if this makes sense if we graph it. So here's my function. Here's A. Here's B. And let me write just, here's f of A. Here's f of B. And z is a number between those two. Right? what needs to be a point on the graph of f? This is a point on the graph of f. F of a. And similarly, here's a point on my graph of f. What are all the points whose y-coordinate is z? Over here. What is this theorem saying? If you gotta go from this point to that point, then somewhere you gotta cross this line. It might be that you cross it more than once, but you gotta cross it at least once. So here would be a value of C that does the job, but on my graph, there seem to be 3 of them actually. But there should be at least one. Okay for everybody on this graph? So if you have a nice continuous function and I gotta go from somewhere below a line to above a line, I gotta cross the line. But do you see why this theorem would not be true if I allow my function to be not continuous? So if I try to graph this the same way, so all right, so here we go, still with our a f of a, b f of b, my value of z. Are there several ways that I could graph a function that starts here, ends there, but does not cross the line? Discontinuous, sure. What if I'm like this? Okay, I did not cross that line. Or what if there's a jump? I don't have it. Not a horizontal asymptote, Vanessa, but what else could you be? A vertical asymptote. So how would that work? Well, suppose there's a vertical asymptote, let's say, at this point, at this line. Right? So what could be a function? Well, what if I have a vertical asymptote like this? Then I never pick up the function value z. Z is never a function value, yet I started below the line and I ended up above the line. That's why continuity is so important in that theory. Okay, so if you're continuous on a closed and bounded interval, then any number between two function values is a function value. Where is about the only time that you might see that, like in on a CSET? If you ever see it, besides a multiple choice question where they just check if you know it, is to prove that an equation has a solution. The first thing you have to do is rewrite the equation in the form of function equal to 0. Then you hope that that function is continuous, but you don't know your a and b yet. So just start plugging in numbers. What you're hoping for is to find a positive function value and a negative function value. And then you can use the intermediate value theorem. Okay, so let's see this in action on one example. And then I'll show you guys how to use the intermediate value theorem to prove there's a solution. So prove that the equation 2 to the x is x cubed has a solution. So proof that the equation 2 to the x is x cubed has a solution. In exercises like this, your first instinct might be, let me just solve the equation. It's always set up in such a way that you will never, ever, ever be able to solve that equation. 2 to the x is x cubed? Sure. If it would have been 2 to the x is x squared, oh, we got lucky, 2 is a solution then. But here, you're not going to see that solution. So the first thing we need to do is rewrite everything on one side. Now that's my function. So put f of x is the function 2 to the x minus x cubed. What is the domain of that function? 2 to the x minus x cubed. It's all reals. So note that f is continuous everywhere or on the interval negative infinity to infinity. So what does that mean? Whatever a and b I'm going to come up with, I have no problems. It will be continuous. So next, what are you starting to do? Well, it's a little bit of scratch work, but start plugging in numbers. What's arguably the easiest number to plug in? Please don't say 2025, yes? So calculate 0. -1, I'm not so fond of negative numbers. So what is f of 0? 2 to the 0 minus 0 cubed, which is 1. That is a positive function value. So what that means is you should now try to look for negative function values. Try some other. What is f of 1? That's also 1. That doesn't help us. Keep looking. Now, if we think about 2 to the x minus x cubed, 2 to the x is an exponential function. X cubed is a polynomial. Which one is typically bigger? The exponential function or the polynomial? The exponential. So if we make x big enough, it's got to start working. Okay, so let's keep going. F of 2 is 2 squared minus 2 cubed is 4 minus 8 is -4. Bingo, we got it. We got a positive function value and a negative function value. So what can I use for my a and my b? One and two. You could also use 0 and 2, but the closer one is 1 and 2. So so in the actual proof, you wouldn't even need this guy. You would have said, hey, scratch work, I'm not going to write this down. F of 1 is 1. F of 2 is -4. So since f is continuous on the interval 1, 2, and f of 2 is less than 0 is less than f of 1. -4 is less than 0 is less than 1. It follows from the intermediate value theorem that if that any number between two function values is a function value. So this here 0 is between two function values. So 0 is a function value. That there exists a C in the interval 1, 2 such that f of c is 0. Let me write out what that means. So 2 to the c minus c cubed is 0. We can rewrite this as 2 to the c is c cubed. Hence, the equation 2 to the x is x cubed has a solution. What is the solution of that equation? That mysterious number c. That weird number c. So the theorem doesn't tell us what that number is, but it's somewhere between 1 and 2. Somewhere between 1 and 2, there's a solution. There could absolutely be more. But we know for sure there is at least one solution somewhere between 1 and 2. Okay, so that's kind of one of these typical math theorems. There exists a solution, but we don't tell you how to find it. So how practical is that? There are methods, then numerical methods, that will find that solutions that use the fact that somewhere between 1 and 2 there should be a solution. Okay, so that's the intermediate value theorem, and that's about the only exercise you could have practically about the mean value theorem. There's some exercises then that I wanted to go over. We'll have to go over those next week from the CSET. We can have a look at them. CSET 6, 7, 8, 9, and 10 are all about continuity and limits. But I think we're going to get kicked out of here in about 2 minutes for it. So let me maybe just check. So in 2 minutes, we'll get kicked out. So let's have a look maybe at just question number 6. Let f of x be the function whose graph is shown above. Which of the following statements best describes why f of x is discontinuous at c? Is it because f of c does not exist? Is it because the limit as x approaches c of f of x is not f of c? Is it because the limit as x approaches c of f of x does not exist? Or because f prime of c is not f prime of c plus delta x? So it's not A because f of c does exist. It is basically because the limit is not a function value. That's the definition of not being continuous. The answer is not C because the limit as x approaches c does exist. And D has absolutely no business here. So what if this function would be changed to this guy here? Like this. What would happen now? The answer would still not be C because the limit still exists. But the answer could also be A now. F of C does not exist. So that's why they had to make sure there was a solid dot there. Otherwise, there would have been two answers. Right? So we're going to get kicked out of here in 10 seconds. Have a good night, and I will see you guys next week. Okay.